Okay, now I will talk to you about something totally different. In fact, while I'm teaching students as well quite a lot, I'm actually in the profession of trying to teach robots. And maybe before we start, I did my PhD in Hollywood, actually quite close to Hollywood. I did it at the University of Southern California. And this is terrible. This is the wrong presentation. That is terrible. So basically what you see here is Hollywood's dream of how robots in the future should work. And as a computer scientist, I obviously would love to see this dream become true. And really ask myself, well, how can we actually realize Hollywood's dream? Now, we can compare this. And we look at the very, very first time where actually people had built a robot. What you see here is in fact from 1969. It's from the time when they built the first industrial robot, and they were so cocky that they thought they would bring this robot, which you will see in a second, directly to your homes, and you will have this robot as a personal robot, or one of its successors, as a personal robot in your home. So they were really so cocky that they thought this would be possible, and you realize that pretty much every single thing in this video is completely anachronistic to today, except for the idea that in the future we should have intelligent robots in our homes to make things work. Their role models are different, their life situation is totally different, their furniture is clearly from the past. But the vision has remained the same. So what actually went wrong here? In fact, our robots today look much nicer. Like the one you have seen in the very first slide. We actually have robots which are much, much more beautiful, which also have some better mechanical function. But pathetically, we program robots exactly the same way as we did this in the past. And if I was today trying to make this video again, it would actually take my students just about as much time as it took those guys back then to program the robot to do this particular kitchen. And even worse, for the next kitchen, we would have to start completely from the beginning. And, well, in order to make the demo work, we would have to start completely from scratch. Now, that's, of course, on the one hand, well, this is, of course, for us from an artificial intelligence point of view, from a robotics point of view, is one of the most pathetic things, how little the field of robotics seems to have moved. Now, what I will, in a few moments, be telling you about is how we can actually go a slightly different way. But first, let's quickly let the video play out. We can program every one of these actions perfectly the same way, just unfortunately, well, with a different script, a different kitchen, and different items. This would be just as hard today as the classical robotics techniques as it was back then. So the reality in robotics is substantially different from the reality which we, well, would like to have. So let's look at the sci-fi scenario again. Why is this so difficult? Well, the first part is we have a lot of uncertainty in the world, and we actually, in order to plan for all the situations, it's literally impossible. Our robots have to adapt to humans, and you should not try this with any of the industrial robots. If you hack one of them, they will most likely crush your bones unless you're perfectly laser scanned. And finally, you see here a programming complexity of these humanoid robots emptying the trash can, which is way beyond any imagination. Now, classical robotics does exactly one thing. They take smart grad students, they put them in a cellar, give them pizza, Coca-Cola, and at the end of the master's thesis, they usually have hacked up quite a good task, like this very first video. But at the next semester, we start from square one, and we are not any smarter. So how can we do this differently? Well, quite clearly, we need learning here. And in this case, I of course mean machine learning instead of human learning. So can robots learn? Well, let's start with a quick view what a robot is. Well, a robot in the end is in a state which it perceives through its sensors, and it will change the state by sending actions or motor commands and which will change the environment. In addition to that, we have a teacher, and this teacher gives our robot a learning signal. Now I'll show you a very simple robot learning scenario here. What you see here is actually one learning scenario one of my grad students created. I had originally asked him to program really good gates for this little walking robot. And, well, as you see, that the gates he could come up with by hand, well, they were pretty pathetic. It fell over and over again. And then I finally told him, well, maybe you should try machine learning for a change. And what you see here is what happens after many hours of learning of the system. And we allowed it to get learning by giving it scores. Just like a good teacher, we give it grades, and we give it a good grade for how far it traveled. We give it a good grade for the velocity it achieves, and we give it a really, really big punishment whenever it falls. And what we basically have here is that in our model, these grades, they're the expected scores of our teacher. Now, we will have two kinds of scores. In the first kind, it's particularly easy because we basically say our teacher shows an example, and this demonstration is used by the robot, and he only gets a score based on the error, on how much difference he actually makes to what happened before. The previous speaker would have called this cloning of behavior, and to some extent this is true. The early methods of learning from demonstrations we used to call behavioral cloning because it really just cloned the behavior without much intent understanding. These days we have slightly better methods there. Now, that of course can't give us everything, right? I mean, otherwise all our students could learn everything from the lecture. They would not require these painful exercises and all of these things. So instead, we need to also learn from experience, in which case the robot has to perform trials, show these trials to the teacher, and receive reward or feedback. Now, let's first go to the question of, well, how can a robot learn from demonstrations? And we should take here a scenario, like a table tennis scenario, where we really want to acquire a behavior, meaning a policy, something which tells us what actions to take in what state, by the teacher showing trajectories or demonstrations, and the student tries to reproduce these as close as possible. Intuitively, this means something very, very simple. Since intuitively, this just means for every action which I've observed, every state and action pair which I've observed, so basically, every one of these little asterisks, we want to reproduce these. Now, if we only care about one state action pair, obviously. If we care about longer trajectories, it becomes a slight bit more difficult. And we can actually do this quite well. So this is a scenario where one of my first grad students, he tried to program this for 1 year with classical programming, and he failed utterly. And then we actually, together with Katarina, another grad student, we sat down, programmed the learning algorithm. It took us 1 month to program the learning algorithm, but the experiment was just one afternoon where it learned it directly from demonstrations. What you see here is the resulting behavior. Now, this is a ball on a string scenario. That's why it's so fast. So we are loading the spring with the energy, and subsequently we keep it in a stable living cycle. So in other words, it seems possible to learn at least elementary behaviors. Now, what can we do now when we want to learn from trial and error, learning from experience, learning from instead of from demonstrations? Well, in this case, we are in the realms of reinforcement learning. And in machine learning, this is actually one of the biggest problems because we don't fully understand how to do it still as of now. But we have a good idea how to do it, not too badly already. And here we really we basically have feedback from the teacher like good student, bad student, where when the student shows to the teacher its particular strikes. And you just get a reward, but you have actually no notion of data in there. So you really need to figure out how you bring data in, and it turns out that there is a very simple way of thinking about this, which comes from psychology, that you really should match your past policies, just reweighted by these rewards, and so that you would reproduce all of the good actions shown by pluses, but if in one case, for one state, you only have bad actions, you rather reproduce this one, and you're a little bit conservative instead of trying something crazily new. And surprisingly, this works quite well. What I'm going to show you here is a scenario which is called kendama in Japan, or bolero in Spanish, or ball in the cup in English, where we take the robot by the hand, we show it a behavior, and we try to reproduce this behavior. But the problem, of course, is the robot is incredibly stupid at this point. It doesn't have hand-eye coordination. It has a 2-kilogram wrist, so it can't produce the same accelerations as the human can produce with its much, much higher acceleration muscles, and henceforth it fails at reproducing this behavior. Now, subsequently, you see how the robot self-improves. And it becomes better and better, really on a trial-by-trial basis, and usually gets the ball into the cup for the first time after about 40-something trials. And more surprisingly, it becomes perfect between 90 to 100 trials. So you can really show a whole afternoon of this behavior, and it won't fail a single time. Now, how does this compare to humans? One of my grad students did non-representative studies on his extended family, and it turned out that the 6 to 8-year-old kids don't manage to learn bolero at all. Already the 10 to 12-year-olds learn it pretty perfectly. So within 30 trials, they get to a rate of 50% success, and grown-ups manage to learn it within 3 or 4 trials. So it seems to be only me who took 3 months to learn it. Now, obviously, we used chocolate as a reward for the family members, and some of the family members cheated, both of which we have never observed with our robots. So now we want to take our robot system and we want to compose more complex behavior. And in order to do this, well, we really need a little bit more structure. And for that structure, we have brought in that we decompose, that we use behaviors like we've learned them before here as primitives, so that you can actually teach in a modular way parts of the curriculum to the robot, show them one type of movement, then another type of movement, and collect, for example, many manipulation movements, where you have grasping, picking up, and so on. Then you have context, which allows you to reuse them in a higher level strategy, and finally, execution. And we want to put, of course, all of this together. Now, this brought us as a first attempt to that we wanted to learn how to teach a robot how to play table tennis. So we took the robot by the hand again, and we showed it, in this case, just a couple of forehands. Now, we want to deal with, different forehands, and in fact, be able to execute them in parallel. So we basically have to learn different primitives for different parts, different incoming balls for the ball gun. And subsequently, we will be able to generalize already by imitation learning. And already by imitation learning, we can do quite well by always incoming ball-dependent recombination of the original primitives. And gets the ball gun already nearly 70% success. But of course, 70% success is, well, not that great. So despite that selection and generalization of these primitives works already quite well there. So we really want to self-improve. And for self-improvement, we can again go towards this reinforcement learning loop. Where in this case, well, we do what a good tennis teacher should do. We aim the ball gun at the regions where the robot is bad at, and where it initially doesn't get a single ball over the net. And you see subsequently how it self-improves. And in this case, because it has so many primitives already, and they work in other parts of regions of the state space, you actually get an improvement quite fast. And from 0% success for that ball gun orientation, you very quickly go to nearly 80%. All over, you actually manage to return 97% of the balls of the ball gun. So it's actually not that bad what you can learn if you target well where you want to play to, and at the same time start with an imitation. Now finally, here you see the robot playing against its maker, and Katharina always wants me to highlight, she's a computer scientist and she learned table tennis for her PhD. So computer scientists are never into sports. And I believe we all agree the robot is about as good as she is. Now, next big question, of course, is how do we create interaction now between humans? In fact, we also have a project even where we want to have joint learning between robots and humans, where both have to learn acquire the task. But this is actually really, really important for us because humans use a lot of human information, about the opponent in this case. So this is a baseball game in Japan. And this here is actually the last moment where this baseball batter will create a single motor command, which depends on the ball. And that's, of course, pretty amazing when you think about it. This is, I would say, about 10 meters away. The baseball bat is a little bit thicker than my arm, and the ball is about like my fist, and the human still manages to hit the ball. Purely based on ball flight trajectory, even with the best possible physics model, he should not be able to predict this. So quite clearly, he has additional information. And it turned out that this kind of additional information actually is present all over in table tennis, and we only learned this when we had invited some European champion in table tennis, and he asked us, why do you have cameras looking at the table tennis ball? You should look at the opponent, you should try to ignore the ball. And we were, what? And he said, yeah, that's what we are teaching kids. So we ended up doing pretty much exactly that, and my Chinese PhD student Jikun Weng actually went into opponent prediction. In fact, this year is the ball, one time where the blue arrow points in the first time, is about 320 milliseconds before he hits the ball. This is, I think, 180 milliseconds, and this is 60 milliseconds before he hits the ball. And already at that time, before he's even touched the ball, we want to predict where he will be playing to. Obviously, the more certain the shorter the time is, the more certain we become, but the earlier we can react, the better the robot can actually do a choice. So what Jikun then trained was a really, really amazing thing. He trained a model where the robot just learned to predict where the human will play to. And we can actually predict with an accuracy of about 30-something centimeters where the human will play the ball to before he has even touched the ball. In fact, nearly a third of a second before he has touched the ball, which is nearly the complete arm movement. And what Jikun then did is he played with the robot and he really taught it some eccentric movements, since movements where the robot really shows, hey, I know where you're going to shoot the ball, and always goes into an awaiting posture when it is fairly certain, and only takes the ball, in fact, when it knows that it knows beforehand where the human intends to play to. Now, how many of you could do this initially? Probably only after some training, the most of you. But we humans are pretty good at predicting other humans, so we decided to now look into how well can we use our machine learning methods, which we normally use for letting robots study, to understand actually what humans are doing. And we obviously took a motor task again, so we took table tennis again. We put different pairs of human players in there, both laymen and experts. The experts were European champion level. The laymen were, people who played once or twice in their life. And we sometimes had the experts playing against each other, sometimes the laymen. And we tried to recover their reward functions. The reward functions which allow us to describe their behavior. And here you see an example of this. It's actually a pretty good example. So we are thinking about this guy wanting to play to the other side. We obviously realize that it would be for him really, really bad. We see here, really, really bad to shoot here, simply because he's not a very good player, and he would probably hit the net if he plays too harshly here, and the ball would never make it to the other side. This is also pretty bad, because this other guy could make a forehand and has an easy time getting the ball. This here is really good for him, because the other guy has to either jump onto the table or run all around it, and has a much harder time of catching the ball. Now, oops, there should have been one more slide. I will fill it in. And it's the most amazing part maybe is that when we looked at the features which were used in there, we actually saw that the European champion level table tennis players had only very, very few differences in their reward function explaining their behavior, and they were literally only about that they would go would be able to go further away from the table, they would be able to deal with higher velocity balls, and they would incorporate the movement direction of the opponent, which basically meant that our learning algorithm figured out that the strategy really depends on your quality of motor levels, and that experts know that they're very good while they have pretty much all the other strategy components are the same between laymen and experts. So, finally, why is this useful? Well, why is this useful? Well, the first and most important part is that we, in the end, really want to bring this to industry. Our robots at the moment in industry are actually made to do the same task over and over again. And they will, and you basically, if BMW tries to make a new, if BMW tries to make a new series, they will actually build a new factory because it's cheaper for them to buy the robot programming together with the new robots from the robot manufacturer than to actually reprogram the robots. That's, of course, a terrible state of the art. If you talk to the companies like Bosch, they will tell you that, well, they rather go to a slave shop in the third world if a product is not at least a little bit expensive, of like 50 euros, and not at least produced about 10,000 times. Otherwise, robot programming is simply the most expensive part of the process. The robot itself doesn't cost that much anymore, especially when you buy it in large quantities. And you can bring it even a little bit further when you look at what people from the second largest robotics company say in the world, that present-day robots are made for repeating the same task thousands of times. Future robots will have to perform thousands of tasks several times. And there's, of course, a ton of other applications. In hospitals, we today use torturing devices for rehabilitation, which perform the same static trajectory over and over again on a patient. This system could adapt to you if it used, for example, our learning algorithms. You could have a surgeon in the future who knows exactly one operation and how to do this exactly really, really well, and there may be 5 in the world who can do it. You could socialize the skill to the complete rest of the world by using robot learning. And in the end, well, for me personally, I think the robot at home, that would still be the absolutely most important task. And with that, I want to close and hope that you maybe have a few questions, since we still have 5 minutes.